Okay, I have shown you the example of virtual work on the beam yesterday, but it may have been too fast, too much for your liking, but simply because I expected you to be able to do things that fast, because one day you will become an engineer. Anyway, I have also wanted to create additional clips to help you through the virtual work on beams as well. So here is the repeat of what we did yesterday. Okay, so this is the beam with the actual load, and after the simple structural analysis, we now know the reactions on both supports as well. So from here, let's give it a name too, so that we can have some reference. And this is A, B, C, and D, just like in the class. So upon using the virtual work, we now know that we need to create the moment equations, right? So I am going to start by writing the moment equation for the actual load case. So from range A to B, it's very simple enough that I have the moment equation equals to minus 1x. Now I still prefer to use the negative sign for my negative moment, and what I mean by negative moment is that I simply use this sign convention. Okay, so that is the negative. So if it is positive, it is of course going to be like this one. Okay, so back to the moment equation. For part BC, there are ways to do it, but as we have discussed in the class, I decided to start at point B for my own benefit in the future when I have the virtual load case. So with this, I can simply write my moment equation starting from point B right away, or I can just cut the free body diagram, which is what I prefer. So when I cut the free body diagram, right here, this is 1 ton, this is 4 tons. So slightly to the right of the support, I will know that I will have here 3 tons. And this is producing negative moment, so I have the moment equal to 1 multiplied by the moment arm, which is 1.5. So this is minus 1.5 ton meter. So moving to the right, I now have the free body diagram with the negative moment with the same amount and the upward shear equal to 3. So my moment at BC, beginning from B, would be equal to minus 1.5 plus 3x, and then again the term from the uniform load, which I forgot yesterday, minus x squared over 2. And for the portion CD, it would be wise to start from D and then moving your way towards C. So my moment equation would simply be equal to minus 0.5x. Okay? So I hope that you realize that the valid range for AB would be from 0 to 1.5, from BC would be from 0 to 6, and from DC would be from 0 to 3. Okay, so let's move on to our virtual load case. So naturally, if you want to calculate the displacement at A, the vertical displacement, you need to apply the unit load. But I'd like to do it in a different way this time, by applying the upward unit load instead of the downward one that I use in the class. And by doing this, I will have the reaction. Let's use the same color. Okay, that is 1.5 downward, and that will be 1.25, and that would be 0.25 upward. So again, by using the same origin, which is of utmost importance, I will now have the moment equation for the virtual load case for the calculation of delta A. Okay, so from AB, Again, this time I now have 1x. It's a positive. So some students ask me if you could use this, as a positive value for the actual case. The answer is yes. But if you use this as a positive moment, this must become negative for you. So it doesn't really matter what sign convention you use. All you need to be is consistent. You need to be consistent, okay? So let's come back here and try to write the moment equation for BC. Again, I can do the same by cutting the free body diagram. So I will have pretty much the same free body diagram, but this time with the 1 going up, 1.25 coming down, and I will have to have 0.25 here going up as well, and this time is a positive moment, you see. So I will have this positive moment equal to 1.5 to complete my free body diagram. So I will move on to the right side of this, and my moment will follow with the same amount, and my shear this time it will be a downward one. So I will have 1.5 as a moment, and then minus 0.25x, okay? And then DC is, well, there's nothing here, so it becomes 0. And I can carry on and do the same for the next case, which is the calculation of the rotation at B. And therefore, I have to apply the unit moment this time, okay? And I apply the unit moment in a way that I have the clockwise rotation, which can be viewed as a positive value. So now I need to have a couple in the counterclockwise direction. So this is going to be my 2 reactions, okay? And by sticking with the same sign convention, oops, let's change that into this one, okay? The calculation for a rotation at B, moment from A to B, well, that's going to be 0. And from B to C, again, beginning from B, don't forget to be consistent, so you need to begin everything from B. I now have the moment equation equals 1 minus x over 6. And from D to C, it's business as usual, which is 0. Now I can move on to the next case, which is the calculation of rotation at C. I can again apply the unit moment, which is positive, which will result in the same reaction, 1/6 here and 1/6 there. So I can now begin writing my moment equation for this case. A rotation at C from A to B is 0. From B to C, because I begin from point B again, so I now only have the shear, which is minus x over 6. And from D to C is again 0. Okay, and the last one, I can just apply the unit load here again, upward, just for, being different, okay? So this guy is going to come down 1.25, and this will be 0.25 going up. So again, the moment equation for this case, which is going to be a deflection at D for AB, that's 0, ladies and gentlemen. And for BC, you only have this load going upward, so it becomes 0.25x. So now I hope that you can assemble your integral and carry out the integration. By saying that, I mean you should know that you need to multiply the equation of the moment from A to B with the corresponding equation from A to B in the respective cases, okay, and then carry out